Hi, my name is Connie Clarnis and you're watching the video Measurement of Strabismus Prisms. In this video we're going to discuss very briefly some important concepts that relate to prisms that we need to know in order to understand how we go about measuring deviations utilising prisms. Now, in the subsequent videos we will be discussing three specific tests that utilise prisms in the measurement of strabismus. The Krimsky, the prism cover test, which includes both the prism alternate cover test and simultaneous prism cover test, and the Maddox rod. Now, you'll recall from previous subjects that when light passes through a prism, it bends or it deviates towards the base. And as such, if we place the prism in front of the eye, it will do just this. The light that passes through the prism will bend towards the base. So the direction of the base in front of the eye is really important. We can clearly obviously hold a prism base out, base in, base up or base down. So we first need to know what deviation is present so that we can then determine the direction of the base of the prism. Let's have a look at a diagram to explain this further. In the first image here we have a patient with a right esotropia, and you'll recall that in an esotropia the contralateral image point falls on nasal retina, and we can see here is the right fovea and here is the contralateral image point, and the contralateral image point is falling nasal to the fovea. Now, if we put a base out prism in front of this eye, what will happen is that the ray of light will deviate towards the base. And this is exactly what we want. We want the ray of light to deviate towards the fovea. Let's look at another example, an exodeviation. In this instance, the contralateral image point is on temporal retina. And what we need is a base-in prism so that the light can bend towards the fovea. So in essence what we're doing is we need the base of the prism to allow the light to bend towards the fovea in all instances. So for a patient with an esodeviation, we always put the base out. For a patient with an exodeviation, we always have the base in. For a hypodeviation, it is up, and for a hyperdeviation, it is down. And what we see here is that the base is always in the opposite direction to the direction of the deviation. So when the eye is in, we have an ESO, the base is out. When the eye is down, the base is up, and so on and so forth. Before we conclude, I just want to make one more point around how we hold prisms in front of the eye. We have two types of prism, glass prisms and plastic prisms, and each have been calibrated so that they are to be held in a particular way in front of the eye. The glass prism has been calibrated to be held in the Prentice position and the plastic in the minimum deviation position. If we take a look at the image to the right here, we have the Prentice position in the first instance, and here we can see that the prism is held in such a way that the line of sight strikes the rear of the prism at right angles. Next to this we have the minimum deviation position, and in this instance the prism is held in such a way that we now have the line of sight making an equal angle on both surfaces here and here. Now, the minimum deviation position would be extremely difficult to maintain in clinic. So instead of using this, we use the frontal plane position for plastic prisms, which closely simulates the minimum deviation position. And so here what we see is that we hold the prism flatly in front of the eye. So for glass prisms we use the Prentice position, and for plastic prisms we use the frontal plane position. And it's important to do this to minimise the errors in your measurements. Okay, that brings us to the conclusion of this video. Thank you for watching.